Welcome back. In the last lecture, we showed that given any ideal I in OD, there exists another non-zero ideal I in OD. There exists another non-zero ideal J. Thus, that I times J is a principal ideal. In fact, the J we took to be equal to sigma of I. Sigma of alpha, alpha belongs to I. And then it was equal to sort of the GCD of the norm of all element taken by elements of I. And we showed that, so this for this sigma of I, if it is imaginary quadratic field, actually it is taking the complex conjugate. So sometimes colloquially this is called I bar. So anyway, I times this sigma of I, this is equal to the principal ideal, and that principal ideal is generated by the element, which is the GCD of all norms of elements in I, in a sense I explained. In fact, then I gave the exercise that, in fact, this will be equal to norm of the ideal. I times sigma I is the principal ideal in OD generated by norm of the ideal, where norm of the ideal is the index of the ideal in OD, which is finite. We have proven in the previous class. And then I give this exercise norm of I into norm of J equal to norm of Ij. Then we consider this relation on the set of non-zero ideals, that I is equivalent to J, I is related to J if there exists some non-zero algebraic integer alpha and beta in OD, so that alpha times I equal to beta times J. And we checked easily that this is an equivalence relation. And I denote the equivalence class. So you define the class group of OD or class group of, actually the ideal class group of OD, or also called the ideal class group of Q root D to be equal to this I, the set of the equivalence classes of non-zero ideals OD. So obviously, if we give such a name, then it should be the ideal class group of OD, sometimes also called the ideal class group of Q root D itself, is a set of these equivalence classes. Obviously, there should be a group structure. So you define I, the class of I into class of J, to be equal to class of Ij. And this is an so check that this is a well-defined operation. So of course, I times J is the product of the ideal, right? So this is again a non-zero ideal. If I and J are non-zero, then I times J is also non-zero, because we are inside OD, which is inside Q root D, which is inside complex number, and the additional multiplication here is of elements are induced from complex numbers. So from there it follows that if you take two elements, non-zero elements, alpha in I and beta in J, then alpha beta is in the product, and that's a non-zero element. So Ij is a non-zero ideal. So so product of ideal, we have discussed finite sum of elements of the from small I to small j, where small I is in capital I and small j in capital J. So this you can check that this is then well defined. So if I is equal to, so alpha I equal to some alpha 1 I equal to some alpha 2 I prime, and beta 1 j equal to some beta 2 into j prime, then you can check that this I into class of ij will be equal to class of I into j prime. Okay, so this will be equal to, this will be well defined. Okay, so I mean one can check using this is a well defined operation. So this is a well defined operation, and then I want to check that. So this is so number one. This is a well defined operation on well-defined binary operation on this. Oh, so this is CLD. Okay, so one needs a notation. Okay, so maybe let's say this is denoted by CLD. Let's say, so define a binary operation on CLD, and then the binary operation is clearly commutative and easy to check that it is associative, and so for any alpha not equal to 0, alpha comes to OD. So you consider the principal ideal that by alpha is the identity element, and so the theorem we have proved, it precisely proves the inverse for any I not equal to 0. There exists J equal to sigma I ideal in OD such that I times J principal ideal. So this is the class of 1 if you like, right? So identity. So this implies that indeed class group of D is a abelian group. Okay, and one of the fundamental theorem is that so observation, even before that observation, CLD is trivial if and only OD is trivial. Okay. So if OD is a PID, that means every ideal is principal. That means this group is trivial, because every the way this equivalence relation is defined, this is the alpha is an identity. Any principal ideal is an identity, because for any principal ideal, I can just take I to be j to be equal to 1 whole of OD. Then any if I take any principal ideal, let's say, right, any principal ideal alpha, then 1 dot alpha is equivalent to OD, right? So which is 1. So alpha is equivalent to 1 clearly. So if this is the PID, then every ideal, there is only one ideal class, namely the principal ideals. Conversely, if it is principal, so then this, on the other hand, if this group is trivial, that means there is only ideal class, namely identity. That means every ideal is principal. OD is a PID. Okay. So one can check that if this is a it's easy to see that if this is trivial, then every ideal is principal. Okay. So this is so in that sense, this measures the obstruction of how far this is away from being a PI. So that means so example and okay. So definition. Okay, so example. So example maybe that class group of class group of CL of, so if you take D minus 1, it's trivial, so ideal class groups of Q group minus 1, Q root 2, and by exercise Q root minus 3. So, or also I'm calling same thing O minus 1, O minus O2, and O 1 plus root minus 3 by 2, or root minus 3, sorry, using this notation, uh, are trivial. And for example, we see that class group of Q root minus 5 is non-trivial. So we have seen this is not trivial. So this statement requires a little bit of work. If this is a PID, you can clearly see it's trivial. And if this class group is trivial, it's not difficult to show that every ideal will be principal. So this statement you can so check. Uh, so this is trivial. So in that sense, this measures so class group uh, D measures the obstruction of OD being a PI. Uh, uh, so more precise is this one. So and so this is a theorem due to Higner that there are only finitely many imaginary quadratic fields Q root minus T for which the ideal class group is trivial. So for example, so a complete list is given by uh, minus t equal to, in fact, there are only 9, and the list is given by this minus d equal to minus 1, minus 2, so q root minus 1 I have said, then q root minus 3 I have asked you to verify, also true for q root minus 2, minus 7, minus 11, 5 is not true. We have seen this is not UFD, so this is not a PID. This class group is non-trivial. Minus 11, it is true. After that, there are 4 other, minus 19, minus 43, minus 67, and minus 163. So these are 9. It's a theorem beyond us. Just as a fact, we'll remember that. I would request you to remember the list. In fact, they are given by d equal to the values of d. It's, there are infinitely many real quadratic fields root p d square free for which class group, the ideal class group is trivial. Okay, there are infinitely many real quadratic fields for which the ideal class group is trivial. Okay, so this is a open question. As you can see, this is quite simple to state, but this is a very deep conjecture which is not been resolved. Okay, and even this is a very deep theorem, the theorem about imaginary quadratic field. It is beyond us. However, at least this is known fact theorem and that so trivial and non-trivial is okay, that for any D class group CLD is a finite. We have already said it's an abelian, so it's a finite abelian. Okay, uh, and definition is that HD class number of root T is defined to be the cardinality of class group, the number of equivalence classes there. Okay, and so HD is equal to 1 if and only if OD is a PI. Okay, on deformations. So what about this theorem? So this theorem we will not cover for every D, but we'll discuss. That's why theorem star. We'll discuss theorem star only for. So we'll say something about this theorem only for imaginary quadratic fields. Okay, so we would like to discuss the finiteness of, we'll say something about it, finiteness of the class group, ideal class group for imaginary quadratic fields. So real will not say. Okay? So we give an example Q root to the ideal class group is finite, and we said that there's a conjecture which is not known, which has not been proved, that there are infinitely many real quadratic field for which the ideal class group is trivial, or HD is 1, or the ideal class group it's a trivial, so it's PID, but it is not known. Okay, so what will be the idea? So the approach is via the approach to discuss the finiteness of the ideal class group is via ideal class group for imaginary quadratic fields, imaginary quadratic fields is via the study of binary quadratic forms with integer coefficient. So we'll discuss binary quadratic forms and the integer coefficient, and via their property we'll say something about. So let me summarize again. So we define the ideal class group with the set of equivalence classes. On the set of equivalence classes of ideals, such that by the relation that for any I is equivalent into non-zero ideals, on the set of non-zero ideals of OD, that I is equivalent to J if and only if there is beta belongs to OD. So the alpha times I equal to beta times J. And this set of equivalence classes is ideal class group. And this ideal class group is known to be finite always. And for imaginary quadratic field, there are only 9 such uh, class groups, 9 such negative integers for which this square free integers for which this class group is trivial. And the infinitely many real quadratic field for which it's a conjecture this class group is trivial. The size of this class group is called the class number. Okay, so what is binary quadratic form? So binary quadratic. So a binary quadratic form is a homogeneous polynomial of degree 2 in two variables. So binary comes from 2 and quadratic means it's homogeneous polynomial of degree 2. Quadratic form means and binary means it has only 2 variables. Okay, so let's say it looks like ax square plus bxy cy square. And so this could be defined over, let's say ABC belongs to R, then so if this belongs to Rxy, the polynomial ring, then we call it then this is a, so let's say fxy, let's give it a name. If this belongs to Rxy, then we say fxy is defined over R. And in that case, you know that so a binary quadratic form. So a binary quadratic form is represented by symmetric matrix form fxy symmetric matrix as fxy xy excuse me xy a b by 2 b by 2 c xy. So this is x transpose to x dash x 2 cross 2 x is x y. Okay, so maybe I should put there a small and a the symmetric matrix. But then we know this that there exists and there exists an orthogonal matrix uh, let's say uh, Q such that Q transpose to Q it's diagonal 2 by 2 matrix. So the R is diagonal and and so then with respect to that, then f of so then so and further eigenvalues are real. and there exists invertible, there exists invertible matrix, let's say S GL2R. Well, invertible is a GL2 is such that S transpose AS is diagonal and have entries plus minus 1. So any binary quadratic form over R is represented by x squared or can be transformed to but this is over here. So this is from linear algebra, I recall, but this is for real cases. So we are interested in. We are interested in ax squared plus. So let's say ax squared plus bxy cy squared to zx. Okay, the polynomials, the coefficients have been set. Okay, so we are interested in such binary quadratic forms. So then definition, let us fxy equal to fxy equal to ax squared plus bxy cy squared and abc and z said to be primitive if GCD of ABC equal to 1. And so if it is not primitive, you can always, a multiple of f will always be primitive. And the definition, discriminant of f, delta f equal to delta is defined to be b square minus 4ac. And definition, binary quadratic form fxy is said to be positive definite if discriminant is negative and it's a is positive and a is positive or c is positive. So equivalently, it is said, so fxy equal to xy into, you have a b by 2, b by 2, c, and xy is said to be the positive definite if a b by 2, b by 2, c is a positive definite matrix. And recall 2 by 2 symmetric matrix A equal to A into in fact R is positive definite if and only if x transpose AX is positive for all x and 2, 1 R, so all column vectors all column vectors in R2 X transpose Ax is positive, so which happens if and only if determinant of A is positive and trace A positive, and that can be if either of the both the diagonal uh, entries are positive in this case. Okay, so the determinant is of course AC minus uh, B square by 4. This is positive. That implies that 4AC minus B square is positive, which implies discriminant P is negative. And of course, A is greater than 0 or C is greater than 0. If this determinant is positive, then this is symmetric matrix. This is equivalent to one of them. If A is positive, then C is positive because trace is positive. A plus C is positive. So these are all equivalent in definition. A greater than 0, C greater than 0, or A plus C is greater than 0. And for that definition, uh, uh, so uh, so so note that if fxy is positive definite form, so I will just write binary quadratic form. So I'll just use the word form. It will always mean in this course it's binary quadratic and it is over z. The coefficients are over z. Then so fxy. So okay. So definition that m in z is said to be represented by a form xy zxy if there exists x and y belongs to z such that f of xy equal to m, I can say alpha. If it takes that value, okay, if for some integer alpha and beta it takes that value m, then you say that represented by a form, or f represents m. Okay. So note that if fxy is positive, then fxy represents only positive, can represent only positive integers. Certain positive integers. It's not clear it will represent certain positive integers. So it cannot represent any negative integers and it cannot even for x not equal to for xy not equal to integers. Okay. Because the homogeneous polynomial, it will obviously represent 0, but if the positive definite form, then it can only represent positive integers otherwise. Okay, so so finally quadratic form said to uh, be properly equivalent to a form form xy xy from gxy if there exists uh, p, q, r, s in z with p r minus qs equal to 1 such that f of p x plus qy and rx plus sy equal to gxy. In other words, says that fxy, let's say, equal to xy and a, b, c, d, xy, and then gxy equal to xy to p, q, rs, a, b, c, d, p, q, r, s, xy. So there exists P, Q, R, S, SL2, Z, 2 by 2 matrix with determinant 1. So this is 2 by 2 integer matrix with determinant equal to 1 such that so G xy equal to xy B transpose xy B xy with so let's call S with B equal to S transpose A S. Then F and G are said to be properly equivalent. Okay, so determinant is 1. So this is due to Gauss. If determinant is -1, then they are said to be improperly equivalent. If determinant is +/-1, then just called equivalent, but we'll stick to this properly equivalent. Okay, so we'll continue on quadratic form next. Thank you.